think we can get started. I think that's everyone we're going to get in. So I might just introduce myself. My name's Suraj. Going to be talking about taking it to the next level. Before I get too started, how many people here have used KVM before? That's most people. And how many have used it on Power? Oh, okay. So all the people I work with, excellent. Thanks for coming, by the way, guys. Yep. So let's get started. This slide's sponsored by IBM Legal. So let me introduce myself first of all. So I live in Canberra in Australia, and I work at Oz Labs in IBM Australia. So I work primarily on virtualization on Power, so that's both Linux KVM side and the qemu side as well, and I've been doing that for about 3 years now. So what am I going to talk about today? So I'm going to talk about nested KVM on the POWER9 processor, which is something I've been working on for about the last year now. Or as I like to call it, KVMception. So what am I going to cover today? First of all, a deep, in-depth look at what is Linux. No, I'm going to skip that one. What I am actually going to talk about is I'm going to give a brief introduction to POWER9 and how it differs to some of the previous Power architectures, mainly in the ways that will be relevant for this talk. Then in case, we've got a lot of hands that people have used KVM before, but just in case, I'll give a bit of an introduction as well and cover some of the ways it works on Power. And then we'll get to the real meat of the talk and what I actually want to talk about, which is nested KVM on the POWER9 processor. So first of all, what is POWER9? So POWER9 is the latest iteration of the IBM Power processor, and you might have seen it features in the Summit and Sierra supercomputers, number 1 and 2 on the top 500 at the US Department of Energy. These are largely multi-threaded processors, and they can run both PowerVM and Linux as their hypervisors. But that's not too interesting. Let's look at some of the interesting changes that occurred in POWER9 in contrast to the previous Power8 processor. So POWER9 was the first processor to have a hardware radix MMU. And what that means is that in the hardware, we're using radix tree translation. This also sits alongside the old hash MMU, which you can still use for hash page table translation. One of the most interesting changes in POWER9, though, is that we now get a single MMU context per thread, in contrast to on Power8, where an entire core had to be in the same MMU context. Now, what this essentially means is that each thread on the core can be executing in a different partition. So if you have multiple threads in your core, they could be executing, for example, in the host, in a guest that's radix, or even in a guest that's running in hash. But what does this actually mean? Well, it significantly reduces the scheduling constraints on our system. Mainly, it means that you can run an NESMT in your host and guest. You can enter and exit the guest at any time you like without having to coordinate with other threads on your core. And the host and guest can be running on the same core at the same time. I'm not sure if any of you know, but on Power8, you had to schedule a core either all go into the guest or all coming out at the same time, and that removes this on POWER9. One of the other important relevant changes on POWER9 is the introduction of this thing called a partition table, which I'll introduce now just so you're familiar with it when it comes up again later. So what is this thing? Well, it's exactly like it sounds. It's a table that exists in memory. The address of this table is stored in the PTCR, or the Partition Table Control Register, so that hardware knows its location. And what it stores is the per partition translation context. So this includes information such as whether the partition uses hash or radix translation. It contains the partition scope translation information, which is managed by the hypervisor, and the process table, or the process scope translation information, which is managed by the guest operating system. Now, the partition table is indexed by the LPID, or the Logical Partition ID, which is a per partition unique identifier. So it could be any number. It could be 0, which is normally used for the host. It could be 1, it could be 5, it could be 127. One's going to be allocated for each guest which will run on the system, and for the host as well. And it's important just that it's unique. So now that's about all we're going to go into on POWER9 itself, and that should be enough for the rest of the talk. Now what I'm going to have a bit of a look at is KVM, just to set the stage for the nested KVM part. And I'm going to focus on the power specifics as well. So we're going to go over what is KVM, some of the terminology, and then the implementation details on power. So what is KVM? KVM stands for Kernel-Based Virtual Machine and is the open source virtualization technology which is built into the Linux kernel. There's support for most architectures and it allows for the execution of multiple and isolated virtual machines. Just a bit of terminology here which will make it a bit clearer what I'm talking about later. So I've got a nice diagram here. Well, nice might be up to debate, but at the bottom we have our hardware and that's our processor that we're running on. And so at the bottom level we have our host operating system, sometimes called our hypervisor, which I'll shorten to HV. And that has its host user space. And if you're running bare metal, that's all you would have on your system. If you're running virtualization, however, you also have these virtual machines or VMs. Now these are our guests or privileged operating systems. And of course, they have their own guest user space. And there could be multiple running on the system at the same time, with the host then mediating guest access to our hardware. So how do we actually run one of these guests? Well, in the host user space, there's a qemu process created when you start up one of these guests. And so when the host schedules that, it then calls back into host KVM code with our KVM run ioctl. If that then decides it's going to enter the guest, it enters via what I'm going to call the KVM entry path, which is just a code path in the KVM code, which loads up our guest context. That way, we're now running in our guest until an interrupt returns control back to our host. When that happens, we take what I'm going to call the KVM exit path, and then we're back in our host again. So let's have a bit of a closer look at this exit and entry path. So as I've called it, the KVM entry path is what we take when we're running in our host and we want to load up our guest context. And now that context is saved in our host memory. So what do we do? First of all, we need to save our host state off the CPU so that we can restore it later when we want to run the host again. We then take the guest state and load it onto the hardware, and off we go. We're executing in the guest context, and that might be in the operating system or in user space. And we can keep running and we can transition between the guest operating system and the user space without any host input. Now interrupts will come along which might return control to the host operating system. These could be hypervisor page faults, decrementers, hcalls, that kind of thing. Now if we can handle that, we can return straight to our guest. However, there might be things that require a full exit to host context for them to be handled. In that case, the guest CPU state needs to be saved off the CPU into memory so we can restore it next time we want to run our guest, and we can restore the host state which we saved before we ran our guest. So now I'm going to give a quick introduction to how memory management works for guests on Power9. I'm going to focus on the radix tree implementation here because that's what we use in nested KVM. We don't support hash yet under nested KVM. So the important thing to remember here is that it's a two-level radix tree translation. Now when we need to translate an address, first of all, what we start with is what we call a guest effective address. And now that's what the program is presenting to the hardware. And it's analogous to a virtual address on x86. Our first translation process is called process scope translation. It's using radix trees which are stored in guest memory, and those trees are managed by the guest to divide its memory amongst its processes. The translation is associated with a PID or a per process unique ID, and the result of this translation process is a guest real address or a GRA. Remember I said it's a two-level translation process, so the second step here is called partition scope translation. This time we're using radix trees which are stored in the host memory and are managed by the host to divide its memory amongst its partitions now. It's associated with this LPID that I introduced earlier, the per partition unique ID, and the result of this translation is a host real address, something which can then be used to access the hardware. Great, but where are these translations actually being stored? Remember I introduced this idea of a partition table, which exists in host memory and is indexed by LPID. Well, it's basically made up of two double words. So first of all, we'll go into process scope translation. So a process table is set up by the guest and registered with the hypervisor, because remember I said the guest manages these translations itself. The location of that table is then stored in the second double word of the partition table entry for that partition. This process table basically contains entries pointing to process scoped radix trees, and that's indexed by PID. And these translations are set up and consequently managed by the guest. What about partition scope translation though? Well, that information is stored in the first double word of the partition table entry. So we have a partition scoped radix tree pointer which points to the radix tree. And this starts empty and is generated or allocated as is needed. So we basically fault in entries dynamically. And it's completely managed by the host KVM code. All right, but how are these translations actually generated? I just said these tables start out empty. So how do we go about creating one? So entries, as you probably all know, are called, in these tables or radix trees, are called page table entries or PTEs. The partition scope PTEs are set up and managed by the guest, and I'm not going to go into this process. What I am going to focus on is the creation of partition scope PTEs, which are managed by the host KVM code. And like I said, these are empty and generated dynamically as we go about running the guest and having to translate addresses. So let's have a closer look at how one of these PTEs is generated. So firstly, we'll have a page fault to the host operating system, which will end up being handled in KVM code. And this is when we need to fault in one of these PTEs in the partition scoped radix tree to translate a guest address. And what we get is a guest real address from the interrupt. We can then use this function guest frame number to host virtual address memslot in the KVM code to give us a host effective address. And this is the host effective address of the qemu process, which is the qemu memory that's been used to then back the guest memory. We then use this other function, find Linux PTE, to find the host PTE in the host process table, which is backing that qemu process. So essentially we've worked backwards. The host has provided some memory to the qemu process, which it's then used to back the guest memory. And we're just working backwards to get back to a host real address. And this actually provides us with a PTE with that host real address, which is exactly what we're looking for. So we can take that PTE now and insert it into our partition scoped radix tree. And that's what we wanted. Of course, there's some bounds checking for things like permission and access bits. And of course, that the page size matches something we can actually insert so we don't map too much memory. Now I hear you all thinking, you've just spent almost 15 minutes talking about KVM and POWER9, and I swear you told us that you were going to talk about nested KVM. When are you going to get to the good stuff? Well, don't worry, that's what we're going to do now. I just had to lay some groundwork in case you weren't familiar with how KVM works on Power. So that's what we're going to talk about. First of all, a bit of an introduction. What is nested KVM? Well, it's essentially a guest which is running within another guest. So what does that mean? So we have a guest and it's able to perform some of the functionality that would normally be performed by a hypervisor. And then it can in turn run its own KVM guests. So as before, we have our hardware and we have our level 0, or what I'm going to call the L0 host now, running on the hardware. We have our same guest we had before, which I'm going to call level 1 or L1, and again it has its own user space. And I've just said that this guest can now perform some of the functionality that a hypervisor would normally provide and run its own guest. So I'm going to call that the level 2 or L2 guest, which is running as a nested guest of the level 1 guest. And as you can see, the numbers will just increase the deeper you get. You get L3, L4. Who knows how deep you can go. Now here are a few of you thinking, maybe, that hasn't this already been done before? I've definitely heard about this nested KVM thing. Well, yes. First of all, you could run a TCG, use TCG to run a nested guest. Obviously, that's not KVM, and it's not going to be very fast. But nested KVM already exists on most architectures, and in fact, it already exists on PowerPC in the form of KVM PR. So here we're going to have to make the distinction between KVM PR and KVM HV. But before I do that, it's important to understand that there are 3 privilege levels that your Power processor can execute in. The highest privilege level is called hypervisor, and that's where your host operating system will run. You then have the next highest level of privilege, which is supervisor mode, and that's where your guest operating system will run in. And obviously, we're decreasing the resources and instructions that can be accessed as we go to lower privilege levels. The lowest privilege level then is problem state, and that's where your user space will run in. Both the host and user space, the host and the guest user space run in this problem state. So now I'm going to introduce the idea of nested KVM PR, where you have your level 0 hypervisor using the KVM HV module to run your level 1 guest. Your level 1 guest runs in supervisor mode and uses the KVM PR module to run its level 2 guest. The level 2 guest now is running in problem state. What this means is that level 1 has to emulate all of the supervisor mode functionality for level 2. You might guess this would be kind of slow, and so I've called it KVM Lite. So what we're actually interested in is this idea of nested KVM HV. And when I talk about nested KVM for the rest of the talk, that's what I'm going to be talking about, this nested KVM HV I'm about to describe. So as before, level 0 uses KVM HV to run level 1. But now level 1 uses a KVM HV module again to run its level 2 guest. What's nice about this is that level 2 is running in supervisor mode. You don't need to emulate it. However, you might need to emulate some hypervisor functionality for level 1 now. But I mean, why would you want to do this? Seems like a lot of work, doesn't it? The main reason is for testing purposes. For example, OpenStack requires a large number of hardware configurations. It means you can test hypervisor changes in a virtualized environment rather than on the bare metal, and it means you can test migration of your hypervisors as well. Additionally, you might already be running virtualized. Say you've bought some time on a cloud provider and you want to test out this KVM thing you've heard so much about so that you can run your own guests. Well, then you would need nested KVM. It's a faster development cycle because it's faster to reboot a virtual machine than is a physical machine, even with all Stewart's optimizations. And finally, because we could. Now here you're saying this nested KVM HV, it doesn't sound so hard, right? You just, load the module and then off you go. Everything, just works. Unfortunately, that's not the case. There's a few puzzle pieces we need to put together here to get this working. And the goal, remember, is to run a KVM HV guest inside another KVM HV guest. So the first puzzle piece is the nested guest entry exit path. Once we're in level 1, how are we going to get into level 2? Once we're there, how are we going to translate these nested guest addresses? And then once we've set up these address translations, how are we going to invalidate them? And those are my 3 puzzle pieces. So the first is nested guest entry and exit. What's the entry and exit path we're going to take? Well, let's have a look at if we could do it with the same KVM entry exit path I introduced earlier. So we're executing in our level 1 guest, and it has its level 2 guest state saved in its memory. So it takes the KVM entry path and tries to load it up onto the CPU. The problem is this requires hypervisor privilege instructions and access to hypervisor privilege registers. And remember, we're running in supervisor mode, so we can't just do this. Of course, we could trap these accesses to level 0 and emulate them. and use that as our method to get into the level 2 guest context. Of course, at some point, we're going to take an interrupt, which will need handling in level 1, because level 1 is providing the hypervisor functionality for level 2, even though the interrupt's delivered to level 0. So again, we can take this KVM exit path, where we need to save the level 2 state off the CPU into our memory. And you might have guessed it, we run into some problems again because there's a hypervisor privilege required to do this. Again, we can trap to level 0 and emulate these accesses. So I've called this the trap and emulate approach, and some of you might have already guessed that this is going to be slow. Every time you have to access a hypervisor register, you're going to have to trap to level 0, which is of course going to mean taking the entire KVM and entry and exit path to get out of level 1 to level 0. And it's just going to get worse the deeper you try and nest. Can we do better? We can paravirtualize this. We can introduce an H-call to make this faster, and that's exactly what we did. We introduced this H-call h-enter-nested, which level 1 makes the call to level 0 and provides the location in its memory of the level 2 state it would like loaded onto the CPU. Level 0 can now use that state in the regular KVM entry path to load the level 2 state onto the CPU and begin executing in the level 2 context. Interrupts which might need to be handled in level 0 can be, and we can return back to level 2 directly. But of course, at some point, an interrupt's going to need handling in level 1, because remember again, level 1 performs most of the hypervisor functionality for its level 2 guest. So what we do is level 0 loads the level 2 state back off the CPU and writes it directly back into level 1 memory. The interrupt number is then given as a return code from the H-call. So what we needed was a nested guest entry exit path, a way to get from the level 1 into the level 2 guest. And we've done this by introducing this H-call h-enter-nested, and so we have our first puzzle piece. But what about nested guest address translation once we're actually executing in our nested guest? So we go back to this model of our two-step radix tree translation, which I introduced before for a normal guest. So when you're executing in level 2, you'll access this effective address, which is again analogous to an x86 virtual address. And we have our two-level radix tree translation again. We have our process scoped and our partition scoped. And remember that we need to set up these page tables in memory so that hardware can find and access those translations. So level 1 has this partition table I introduced earlier, which is used to set up mappings for its level 1 guest real address space. Level 1 is taking on some of the hypervisor functionality, and so it also allocates one of these partition table things, so it can set up mappings for its level 2 guest real address space. And it now has to register this with level 1 via an H-call. But there's only one PTCR. Hardware can only know about one partition table. We could switch the pointer, but then we'd have to flush all of the hardware caches, so this would be slow and inefficient. It's also important to remember that the level 1 partition table only does a single level of translation. Currently, when we've just been running normal guests, we have our level 1 partition table doing translation from level 1 guest real address to level 0 host real address. And so in the level 1 partition table, we have the partition scope translation again, doing level 2 guest real address to what level 1 thinks is a host real address, but it's actually just a level 1 guest real address. So what we need is the entire translation contained in a single tree. The partition scope translation needs to do the entire level 2 guest real address to level 0 host real address translation. So how are we going to do this? So Oh, it's okay, Mikey's have a cough. So hardware is only ever made aware of the level 0 partition table. As far as it's concerned, the level 1 one doesn't exist. We do use it in KVM code to look at these translations, but hardware doesn't need to know about it. So we always just use this level 2 partition table, which now contains entries for both normal guests and nested guests. So what do we need to do? We need to allocate a shadow LPID for our nested guest. And this is the same as any other LPID. We're just calling it a shadow LPID because it refers to a nested guest. And we then allocate an entry in the table for our nested guest. For example, level 1 might be using LPID 2 to run its guest, and it has an entry in its partition table. And level 0 might allocate LPID 3, just because that happens to be the next free one, and allocates an entry in its partition table for its nested guest, or the level 2 guest running under level 1. So let's look at how process scope translation is going to work for this nested guest. So level 1, as I said, has to register its partition table with level 0. So when we're running in level 0, we know the location of this. So we can just copy the process table entry from level 1's partition table into our partition table at the location that we allocated for that nested guest. Now remember, the process table's in level 2 memory. It's indexed by PID, and there's a radix tree per process. But the important thing here is that these translations are all managed by the guest operating system, here the level 2 operating system. And so we actually get it for free. We don't need to translate any of these addresses, and we don't need any hypervisor intervention. We just copy the process table base across, and then hardware can do the rest for us. What about partition scope translation? That's where it gets interesting, as always. So we have our partition scoped radix tree for our nested guest, which is in the first double word, as I said, and here it's at the place, the index we allocated for our shadow LPID for our nested guest. And I said we need to have a mapping from level 2 guest real address to level 0 host real address. Now remember, these trees are normally empty, and when hypervisor page faults are generated to level 0, we're going to fault in one of these entries. The exact same thing we did for a normal guest, but now we're doing it for our nested guest. So how do we construct the shadow page table? Well, let's have a look at what happens when we take a page fault for one of our nested guests. So as before, the page fault provides the guest real address, and here it's a level 2 guest real address. So we need to translate this into a level 1 guest real address first. And what do you know? That mapping is contained in the level 1 partition table. We know where it is because level 1 registered that table with us. And so we can just go walk that radix tree in software. And that will give us a level 1 guest real address. Of course, we might get to the bottom of our radix tree and find that there's no PTE there. So what are we going to do? Well, we can synthesize an interrupt to the level 1 operating system. It should go handle that interrupt just like any hypervisor would for its guest, and should fault in a PTE. And then we can retry next time the nested guest tries to access that address. So now we have our level 1 guest real address. We need to translate that into a level 0 host real address. And so now we're going to use the level 0 partition table, or the radix tree that it's set up for that level 1 guest. And again, we can just walk this in software. And that will give us our PTE with our host real address. Of course, again, there might not be a PTE at the bottom of our radix tree, but we're the hypervisor. We know how to set up those entries for level 1, and so we can go and do that, and then do the translation and also insert the nested PTE. So there we go. We take our PTE, and again we insert it into what we've called the shadow page table, and again with bounds checking, of course. So just a quick overview in case that went by a bit too quickly. A level 2 guest accesses an effective address, And the hardware MMU uses the level 2 process scoped radix trees to generate a level 2 guest real address. That then goes back through the hardware MMU again and is translated through our shadow page tables, which we set up for our nested guest, into a hardware address or host real address used to access our memory. So I said we need to be able to translate nested guest addresses. And we get process scope translation basically for free. And we set up this shadow page table, or just another partition table for our nested guest by allocating a shadow LPID. And that's the second piece of our puzzle. So we've seen how we set up these translations, but how are we going to invalidate them? Unfortunately, sometimes you need to tear these trees down. It's always a two-level radix tree process, as I'm sure you're understanding by now. So let's look first of all at level 2 invalidating a PTE in one of its process scoped radix trees. Well, as I'm sure you also remember, these trees are in level 2 memory, and so level 2 can just go and invalidate the PTEs in memory itself. Level 2 also runs in supervisor mode, and so is capable of using the supervisor privileged instructions to invalidate the hardware caching of these translations. And so when no assistance is required, level 2 and lower level guests are able to manage their own process tables and translations just as any other guest could, without any host intervention. Where it gets interesting is again partition scoped invalidations. And there's two cases here. The first is level 1 invalidating a PTE in one of its partition scoped radix trees. Now that page might have then been passed through by level 1 to one of its level 2 nested guests. And so the corresponding PTE now must be invalidated in the level 0 shadow page table, otherwise the nested guest can just go still access it, which is kind of a problem, as I'm sure you'll see. Now the instruction to manage the caching of partition table translations is a hypervisor privilege instruction. So we had two choices here. We could either trap to level 0 or we could just make an H call. And we figured since we already had an H call for the entry and exit, we may as well have one for this as well. So when level 1 wants to invalidate these entries, it needs to make an H call to level 0, providing us with a level 2 guest real address. The shadow page tables are keyed on level 2 guest real address, and so we can just walk them and invalidate any PTEs we may find as the hypervisor and issue the instruction to hardware to invalidate its caching of those. The second case is level 0 might invalidate a PTE in its partition scoped radix tree for the level 1 guest. Again, that might have been mapped through to the nested guest of that guest. The problem here is that KVM code only provides us with a level 1 guest real address. And I've just said that these shadow page tables are keyed on level 2 guest real address. So we can't just walk it and see if there are any PTEs there. To solve this problem, we introduced the idea of a reverse mapping, or an R-map. And what this essentially contains is the level 1 guest real to level 2 guest real address mapping. And one of these is created whenever a PTE is generated in the shadow page table. What this means is that when we come into the KVM code with our level 1 guest real address, we can look up this R-map and see if that level 1 guest real address has been mapped, if that level 1 guest real address corresponds to any pages which have also been mapped through to a nested guest. And we can get our level 2 guest real address back. Then, just like before, we can walk our shadow page table and invalidate any PTEs we might find and invalidate the hardware caching of them. So I said we need to be able to invalidate the translations for our nested guests. And level 2 gets to do that directly, just as any other guest. And we handle these shadow page table invalidations with this thing called an R-map. And so that's our third puzzle piece. We can now run our nested KVM HV guests. Yay! All right, so I've gone through the implementation of nested KVM HV on the POWER9 processor. Now that we've done that, I'm going to look at some of the interesting features that this implementation brings about. The first is nested-nested. Our level 1 guest was acting as a hypervisor for its level 2 guest, so that level 2 guest can now act as that again and run its own level 3 guest. Level 1 will maintain shadow page tables for level 3, and level 0 then sees level 3 as just another guest of level 1, and so we'll maintain shadow page tables for that as well. I'm sure you're seeing there's going to be a lot of shadow page tables here, but that's an unfortunate side effect of the implementation. So what that means is that it's theoretically possible to nest indefinitely, given enough memory that is, and time, and there's a few caveats. What we also get is migration of nested guests. When you migrate your level 1 guest, if it has nested guests below it, they'll just kind of come along for the ride. The state of all the level 2 guests is stored in the level 1 memory, and I mean, that's already the main part of the migration stream. All of the level 0 state for a nested guest can be reallocated or regenerated on the receiving side, except for one thing, being the location in level 1 memory of its partition table. And so we just add that one thing to the migration stream, and then we get migration of nested guests for free. Another interesting thing you can do is migration between levels. Level 1 and level 2 guests are both just P-series guests. So you can take your level 2 guest, migrate it up to level 1, and if you please, migrate it back down to level 2 again. You just need some transport between level 1 and level 0. You can also do pass-through of emulated MMIO. So if you have level 0 emulating a device for level 1 just sees that as a real device, and so can pass it straight through to level 2. So now, level 0 traps those accesses and emulates the device for level 2. This is pretty useful for testing. If you don't have a real device and you want to test pass-through of it, you can emulate it first and then pass it through at the next level. But here you're still saying, that sounds like a lot of work you've done here. Did you actually get any benefits from it? So here I've ran a kernel compile test and tested native performance, a level 1 KVM HV guest, and then the 2 nested KVMs I talked about, KVM PR and HV. So you'll see we take about a 20-second hit from native to our first guest, but then we only take about a second when we go to our nested KVM HV guest. And you'll see it definitely performs better, as we expected, than our nested KVM PR guest. Now, the one question you all actually came here for, of course, is, but how deep can you nest? Well, I managed to boot a level 11 guest before I saw significant slowdown. So it was when you're booting level 12, it got almost pretty much unusably slow. This is due to the exponential effect of when you're bouncing around H calls between levels. But I mean, I can't see a good use case for a level 12 guest anyway. So what's the state of the code? So this code is all upstream as of Linux 4.20 with some bug fixes merged recently, and the qemu side is upstream as of 3.1. How do I use it? So in level 0, you just need to make sure you enable this nested KVM HV module parameter and then turn on the nested HV cap on your qemu command line. In level 1 in the kernel, you just need the patches, but then there's no specific steps required to enable it. And your level 1 qemu and level 2 Linux don't need anything special. What future work is there to be done here? Well, of course we could optimize it so you can run lower than level 12 guests, but I'm going to need a good use case before I spend any real time on that. It'd be nice if we could run hash page table guests at the bottom level alongside their radix counterparts, and we could possibly look at emulating the H-enter nested H-call for TCG guests. But again, I struggle to see use cases for that. And that's everything. So I hope you enjoyed the talk, and I'm happy to take questions if there are any. Well.
There we go. If you're achieving isolation with KVM, how do you gain any value at all by nesting it?
In terms of isolation,
that is, if it's working, you shouldn't have to nest. If it isn't working, then you could be gaining some value by nesting. So what's not working that makes you want to nest it?
So you're not gaining any benefits in terms of isolation by running as a nested guest. The main reason you want to run a nested guest, like I said, is if you're already running under KVM, you've bought some time on a cloud provider and you want to run KVM, or if you want to test, maybe you just want to run other operating systems for testing, for example. OpenStack runs virtualized and then wants to run KVM guests below it. Oh, Stuart, do you have something?
Yeah, OpenStack does it, and they're isolated from testing, so you isolate your pull request from OpenStack for running virtualized. To be a first-class architecture in OpenStack, you pretty much have to do nested because they want to isolate when they're testing their code in a guest, so it's not attacking the bare metal, but you still need to launch virtual machines because you're testing your cloud software, so they need to do nested.
And because we could.
I just want to say thanks. That was super interesting. You started off by talking about trap and emulate.
Yes.
That just seems way simpler. Do you have performance numbers on that? Like you could do the emulation by just creating way more L1s?
I don't have numbers on it, but the slowdown wasn't. You got a little bit of performance impact by using the H-call. Once you're in the nested guest, right, performance, you're running either way on the chip. So it's entry and exit paths. So if you have a lot, as you get lower down, you're going to have to do a lot more emulation. And so it's a lot slower. So it's just quicker to have this H-call, and it just worked out easier. But yeah, like you say, the first approach I took was the trap and emulate approach. Any register access or anything was done with trapping. It just seems simpler in the end to use the H-call and paravirtualize it. And we use the H-call again for the TLB invalidations, again, just because it's easier.
So it sounds like you've got a really friendly architecture to virtualize. Were there any other sensitive instructions you needed to trap and emulate, or vvite or anything?
No, so the three we ended up having to trap and so it was all the registers on the entry and exit path. There was the TLB invalidation instruction, and it's a bit far out of my memory at the moment, but I believe there was one more, but no, it was mainly register accesses and like HRFID, which is the instruction actually used to get into the guest. Yeah, that was about it.
I have a question about the partition table.
Yeah.
Basically, I'm familiar with Axis, but I'm not Power. Can you briefly explain what is the purpose of the partition table? I mean, you have the process table, right, and the partition scoped table.
Yep.
So I understand that the radix tree is basically the page table on the x86.
Yep.
But you know, so what is the partition scope that page table? And the other question is, do you have, you know, let's forget about the nested. On Axis, we have EPT, right, for the interprocess, which is used to translate the guest physical address to host, you know, physical address. And so on the Power, do you have something similar or no?
Okay, so I think I'll start with the second question. You said you have an EPT which translates a guest real address to a host real address, was that correct? So that's what the partition scope radix tree does. It does that level of translation, and the process table does the guest virtual or effective, depending on what you want to call it, to the guest real. As to why we have a partition table, for example, if you look on Power8, there's what's called an SDR1, which is the location of the hash table in memory. And if you want to run a guest, you had to switch that pointer, which meant invalidating all your caches. So what the partition table means is, instead of having to switch that register, the hardware takes the LPID and indexes the table to get the translation information for that partition. So instead of updating registers and invalidating caches when you want to run a different partition, that information is all stored in memory, and you just update this LPID register, which just indicates the number of the partition you're running, and then the hardware goes and finds the correct trees in memory from the partition table. So it's a way of storing multiple translation contexts in memory, and hardware can go and find them and in fact cache multiple of them at a time.
Unfortunately, I think we now are out of time and have to get ready for the next session. But thank you very much for a very interesting talk and a small token of appreciation.
Thank you.